Welcome to School of Computing. In today's session, we will be discussing red-black trees. Red-black trees are an advancement to AVL trees. In our previous discussion, we have seen AVL tree, we have also constructed AVL tree, we have also implemented it using C programming. AVL trees are extremely good when search operations are frequently done on the tree, whereas AVL trees are not good enough if more frequently insert, delete or modifications are done on the tree. So when you are frequently doing insert, delete or modification operations, instead of AVL tree, red-black tree is recommended. Red-black tree offers you better performance than AVL in insert, delete, modification operations on a tree. So depending upon your requirement, if more frequently search operations are done, means in search applications AVL trees are really good, whereas if more frequently the data gets modified either because of insertion or deletion or modification, then red black trees are better, because in AVL tree whenever we insert, delete or modify, it leads to rotations, and rotations will consume time, whereas in red black tree we use a concept of color. We give colors to every node, either red or black. In red black tree also rotations are involved, however the number of rotations will be less because of the color concept, and hence when compared to AVL tree, red black tree is recommended and offers you better performance in applications where more frequently insert, delete or modifications are done on the tree. So we will try to understand the construction of red black tree, and in order to construct a red black tree we need to know certain properties of red black tree. Point number 1, color property. Every node is either red or black. Every node is either red or black. Root node is always black. Root node is always black. Leaf nodes represented as nil or null is also black. So the point to be noted is, here the null node means the node which does not even exist, means already we have leaf nodes. Leaf node means node without any children. So the so-called leaf node whose children do not exist, we call them null nodes, and null nodes are treated as black. When the node does not exist, why are you treating that node as black? This could be a question or confusion in anybody's mind. Why a node which does not exist is treated as black? We will understand its importance during our red black tree construction process. Another important property is, in a red black tree no two consecutive nodes are allowed to be red. No two consecutive red nodes are allowed, or else you can say parent and child both can't be red and red. So if there is two consecutive red nodes, then it is a violation of this important property and the tree is not called as a red black tree. So we need to make sure that two consecutive red nodes are not there. If two consecutive red nodes are found, then we have to alter the tree, we have to perform certain operations. So when red violation occurs, what need to be done, we will understand during the construction process. Another important property, in every red black tree, from the root node to leaf node, the number of black nodes must be same. For example, if I have a root node and 3 leaf nodes, from root node to every leaf node, the number of black nodes present in the path must be same. Otherwise, the red-black tree constructed by you is not correct. So with this few important rules, we try to construct a red-black tree using by applying all these rules. So we will move on and we will start constructing a red-black tree. So for example, the data is 10, 20, 30, 40, 50, 25. You can take any sequence, you can apply the rules of constructing the red-black tree, and finally we need to make sure the tree constructed is valid. So every red-black tree is a binary search tree. So this is an important point. Every red-black tree is a BST. So while constructing the tree, I need to follow this rule. So I am constructing a binary search tree only. So let me begin with the first node. What is my first node? My first node is 10. And if you remember the rules, the root node is always black. So my job is to give color to every node, and by default the root node is black. So let me mark it as black. What is the second element? Second element is 20. 20 is greater than 10, so it appears on the right side. Every newly created node is marked as red. Every newly created node is marked as red. Now if you look at this particular tree, there are only 2 nodes and one is black, the other one is red. So as of now it does not violate any rule of RBT, and this is fine. Now let me continue the process and insert the next element. So existing tree is like this: 10, which is black, 20, newly created node red. Now I need to insert the third element, 30. Every newly created node is marked as red. Now here if you observe, there is a violation. The violation is 2 consecutive reds. Parent and its child both are red. 2 consecutive reds appeared. When 2 consecutive reds occur, it's a violation of our RBT and we need to do certain operations. What need to be done? So please observe. When two consecutive red nodes appear, what we have to do? We have to do either recoloring or rotation. So when 2 consecutive red nodes appear, we have to do either recoloring or rotations. Now the point is, when should I do recoloring and when rotation has to be done? So please try to understand this point carefully. Observe the example. So when only 10 and 20 was there any violation of RBT? No. So this is fine. Problem came when 30 was inserted. So the problem came because of 30. So who is the culprit? 30 is the culprit. And two consecutive reds appeared here. Now what you have to do is you have to do recoloring. When you have to do recoloring, try to understand the point here. Recoloring is done when uncle is red. So what do you mean by this? This is an important point you need to understand so that you can properly construct a red black tree. When uncle is red, you have to do recoloring. So what do you mean by uncle is red? So when I say uncle is red, it means uncle is also a node. So what do you mean by uncle? Who is uncle? Uncle refers to what? Uncle is nothing but sibling of parent. Uncle is sibling of parent. Now look at the problematic node. What is the problematic node, or the node which created the problem? 30. Who is the parent of 30? 20 is the parent of 30. Then who is called as uncle of 30? For example, if there is another child for 10, let us say 5 is another node. So what is the relationship between 5 and 20? 5 and 20 are siblings. 5 and 20 are siblings. So for 30, 5 becomes uncle. Got the point? So uncle means sibling of parent. But in our example here, do we have sibling for 20? 20 is the only child of 10. There is no sibling for 20. When there is no sibling for 20, then automatically 30 will not have any uncle. Now here comes an important point. So uncle exists or not? In this case, uncle is not there. No uncle. Uncle does not exist. When a node does not exist, it is treated as a null node. Yes or no? In the rules we have seen, when a node does not exist, it is called as null node, and all null nodes are treated as black. Null nodes are treated as black. So now I repeat, 30 is my node which created the problem. RR violation occurred, red violation, and 30 don't have an uncle, so uncle is not there. When uncle does not exist, straight away it is null node, and when it is null node, it is black. So here what is the conclusion? Uncle is black. So when uncle is black, we do rotation. So when we will do rotation? When uncle is black. So when we will do recoloring? When uncle is red, we do recoloring. When uncle is black, we will perform rotation. So what is the summary? So now you understood what do I mean by uncle. So uncle red, we do recoloring. Uncle black, we have to perform rotation. So before we perform these operations on our example, we need to get complete clarity on what is recoloring and rotation. So whenever we use the word recoloring, whom do we recolor? Recoloring should be done on uncle. Uncle is a node, right? So it has to be recolored. Recolor the parent node, and recolor the grandparent also. So please remember, when we are recoloring, we have to recolor three nodes: the uncle itself, parent and grandparent. And when we use the word rotation, remember, whenever, wherever in data structures you come across the word rotations, the moment I use the word rotation, you have to apply AVL rotations only. So whatever rotations we have seen in AVL, same rotations will be applied in RBT also. So let me continue with the problem. So what was our problem? 10 was a black node, 20 was a red node, 30 was also a red node. So there was a violation. Now I need to find who is uncle of 30. Uncle does not exist. Uncle means it should be a sibling of parent. Parent is 20. 20 is a sibling means another child of 10. So we don't have any other child of 10. So uncle does not exist. So in this case, what is happening, sir? Uncle does not exist. So uncle is not there. When uncle is not there, it is nothing but uncle is black. So in uncle black situation, what we will do? We will do rotation. Now look at this example. So when I conclude that I need to do a rotation operation, I will apply my standard AVL tree rotations concept. Now look at this problem as an AVL tree problem. So what type of problem it is? For a moment, forget about this color. Now it is what type of problem? Problem occurred on the, from root node, if you observe, problem occurred on the right side. And problem occurred because of a right child. So it's a RR rotation problem. It's a RR rotation problem. When there is an RR rotation, what we will do? We perform a left rotation. We perform a left rotation. So I will be doing left rotation here on 10. So what will happen? What is going to happen? What is the output? The output is 10 will come here, 20 will climb up, now if you observe the previous colors of the nodes, 10 was black, 20 was red, 30 was also red. Now what will happen? We have done rotation. In that process, 20 became a root node. So since 20 got promoted as root node, its color will become black. Actually it was red. Why it became black? I am not doing a recoloring because I have done a rotation, and since 20 was promoted as root node, 20 was made black and 30 as usual red. Now there is another important point. 10 which was previously black will also be made red now. You may ask why. The reason is, when there is a node, black color node, and it has two children, both children should be of red color only. 30 is already red, and hence 10 is also converted to red. So this is the current situation after performing rotation on the previous diagram. So now this is fine. Now what I will do? I will try to insert my next element. I hope you remember the sequence. What is the sequence? 10, 20, 30, 40, 50 and 25, right? So let me insert the next element. Where next element gets inserted? 40 will be inserted here. And every new node is red. 40 is also red. Now again two consecutive red nodes appeared, so it's a problem. Now I need to check who is uncle of 40. Now in this case, for 40 there is an uncle. Who is the uncle of 40? Uncle definition is sibling of parent. 40's parent is 30, sibling is 10, and uncle is existing now. What is the color of uncle? Uncle is red, and you know very well, when uncle is red, what we have to do? We have to do recoloring. And you remember, recoloring means what will be done? Uncle will be recolored, parent will be recolored, and grandparent. So in this case, we have to recolor 10, we have to recolor parent. 40's parent is 30, we have to recolor 20 also. So then how my output will look like? 20, 10. 10 is the uncle which has to be recolored, so red will become black. 30, which is red, it also need to be recolored, so it will also become black. 40 will not be disturbed, it will remain as red. And as per recoloring rule, what need to be recolored? Uncle, parent, and grandparent. So uncle 10 was red, I made it black. Parent 30 was red, I made it black. And grandparent, who is grandparent of 40? 20 is the grandparent. Grandparent 20 was black, I'll make it red. But you know very well, root node should be black. So once again, since it is root node, I'll make it black again. If it was not root node, definitely its color was, we have to modify it. Since it is root node, even though it was converted to red, we again make it black because it is root node. So if you observe, this is the current status after inserting 40. So I hope you are following me, and till this part things are clear to everyone. So we will continue the insertion process. Till now we have inserted up to 40. So we will try to insert the next element. So this is my current status, right? So this is the latest tree. 20 is the root node, color is black. 10 is also black. Then 30 black, 40 is red. I am inserting the next element 50. 50 is a new node, and every new node should be marked as red. We have done it. It created two consecutive reds problem. But if you observe, 50 is my problematic node, right? Who created problem? Previously this was absolutely fine. The moment I added a 50, it created a problem. So now from the problematic node, you have to see who is the uncle of problematic node, or the node which created the problem. Means who is uncle of 50? Uncle of 50 means he should be sibling of the parent. Who is parent of 40? Who is parent of 50? 40 is the parent. Do 40 have any sibling? Sibling means what? 40's sibling means another child of 30. So do I have anything like this? Do I have anything like this? As of now, we don't have any other node as child for 30. So only child for 30 is 40. So there is no sibling, means for 50 there is no uncle. For 50, is there any uncle? No uncle. No uncle means what? It is same as uncle black, right? It is same as uncle black. So when we say uncle is black, what we need to do? We need to do rotation. We need to do rotation. Now the moment I say rotation, I will be applying AVL rotation. So this is my problematic node. Now please observe only this portion of the tree, right? So if you remember the concept of AVL rotations, from problematic node we will take the previous two more nodes. Means in AVL terminology we call this one as key, and this is the actual node, this is node hyphen right. So these three nodes only you need to observe. And what type of problem it is? Rotation means what type of rotation issue it is? It is RR rotation, right? Problem occurred on the right side of the tree and because of a right child. So it's a RR rotation problem. So what we will do, we will perform a left rotation. So we will perform a left rotation on this part of the tree. So please observe, only on this part of the tree we do a left rotation. Means 30 will be shifted to left. So it will look like this. 30 is shifted to left side. 40 got promoted. And 50 sits here. Since 40 got promoted and its color will become black, 50 remains red, and since 50 is red, 40 is black, black nodes both children must be red, so this will also be modified to red, and remaining part of the tree will be like this as is. 20 which is black and 10 is also black. So this is the status of the tree after inserting 50. So till this point I hope it's clear. Now what is the next element to be inserted? Next element to be inserted is 25. Next element to be inserted is 25. So let us try to insert 25. So as per this diagram, where 25 will be inserted? 20 is black, left side of 20 is 10 which is also black, right side we have 40 which is black, 40's left side is 30 and 50. So 50 is red in color, 30 is also red in color. Now I need to insert 25. Where 25 will be inserted as per binary search tree rule, 25 will become the left child of 30 because it is less than 30. So 25 will appear here. And every newly created node will be marked as red. 25 is also marked as red. Now if you observe carefully, two consecutive red problems appeared. Now again I need to check what is the status of the uncle. So what is the node which created problem? 25 is the node which created problem. So who is uncle of 25? Uncle of 25 is sibling of its parent. Who is the parent? Parent is 30. Sibling of 30, do we have a sibling? Yes, we have a sibling for 30. Sibling is 50. So for 25, is there any uncle? Yes, there is an uncle, and uncle is node 50. And what is the color of node 50? It is red in color. And you know very well, when uncle is red, what need to be done? Uncle red. What we have to do? We have to do recoloring. Recoloring on what? We have to recolor the uncle itself, parent and grandparent. So let me apply this rule. So what are the nodes which are going to be recolored? Uncle will be recolored, parent will be recolored, 25's parent is 30, grandparent will also be recolored. Here grandparent of 25 is 40. So if I apply that rule, right, look at the latest one, 20 black, 10 black, these two are not modified, 40, so 40 is the grandparent of 25, it has to be modified, right? So 40's existing color is black, so it will become red now. And 40 has two child nodes, 30 and 50. So since 50 is the uncle need to be recolored. 50 was previously red, now it will become black. 30 was previously red, now it will become black. 25 will remain as it is. What is color of 25? It is red. So this is the final insertion, because my input was 10, 20, 30, 40, 50 and 25. I have performed RBT construction by following those properties, like root node must be always black, 2 consecutive red nodes are not allowed, right? So those things we have followed. Now interesting point is, who will validate this one? Who will validate this one, or how you will say that this final RBT construction is correct? So you need to validate your RBT by following one simple rule. From root node 20 to every leaf node, how many black nodes are coming, you have to check. And the number of black nodes from root node to leaf node must be same. So how many leaf nodes are there in this tree? 10 is a leaf node, 25 is a leaf node, 50 is a leaf node. So 20 to root is 20, right? This is root node. So 20 to 10, how many black nodes are found? 2 black nodes, right? And from 20 to 25, if you observe, 20 to 25, what is the path? 20 to 40, then 40 to 30, 30 to 25. So in that process, in that path, how many black nodes I am finding? 2 black nodes. That's great. Then 20 to 50, another leaf node. How many black nodes you are able to see? 20 to 40, 40 to 50, 2 black nodes. So from root node to every leaf node, if you observe, the number of black nodes must be same. Number of black nodes must be same, right? So this is a proper binary search tree, and the number of black nodes from root node to every node, every leaf node is same. 2 black nodes in this example. So this tree is a proper red-black tree. So I hope you understood the process of constructing a red-black tree. So red-black tree has got lot of useful applications. So this is very, very important. Applications of RBT. Many real-time applications. For example, there's a very popular programming language, C++. We all know it's an object-oriented programming language. C++ has a concept called as a standard template library. We call it as STL. STL is implemented using RBT. STL is implemented using RBT. Similarly, in Java, another famous object-oriented programming language, we have a concept called as map data structure, hash map, tree map. That map concept is implemented using RBT. In operating systems also, RBT is used, especially for memory management, in virtual memory concept, etc. So there are lot of useful real-time use cases and applications of red-black tree, and hence one should know clearly the construction process of red black tree and also the implementation of red black tree. You can implement this in any programming language. We try to implement this using C programming language in our upcoming session, but red black trees are very important and they are efficient, especially when more frequently insertion, deletion and modification operations are done on the tree. Suppose if the requirement is search operations, means the modifications are less frequent and more frequently you perform search operations. In that case, AVL tree is recommended. And if you have more modifications to be done, AVL becomes costly because of rotations involved in it, and hence RBT is recommended. So both has got their own applications. Depending upon the requirement, we have to pick the suitable tree and we have to apply the same. So before we summarize, so what exactly we have discussed in this session, we have discussed how to construct a red black tree, what is the purpose of red black tree, and the real time applications of red black tree. So I hope you have understood the process of constructing a red black tree, the step by step process, by considering all rules and regulations of red black tree. And in the upcoming session, we will discuss the implementation of red black tree in C programming language. Thank you.